It's an honor and a pleasure to be here with you all today. Yes, so the plan is to talk about spectral geometry of arithmetic manifolds. But arithmetic manifolds are, sort of a complicated kind of thing. It's not usually defined, or it's hard to sort of find maybe a lot of people who know what these things are. So my goal for today is to primarily talk about arithmetic manifolds, what they are. So, but let me start with a little bit of motivation. So, just the big picture of what I'd like to talk about between this and the next lecture is for, say, M compact hyperbolic So some questions. So, okay, if it's compact, there's lots of geodesics on this manifold. So the question is what information is contained in the links of these closed geodesics? So what info is contained in the links of closed geodesics? Hyperbolic manifolds sometimes have totally geodesic surfaces, and you might also be interested in what kind of information is contained inside those things. So, sort of a higher dimensional version is what info is contained in totally geodesic surfaces. And if you have geodesics and totally geodesic surfaces, and you might be interested, and this is something I'm particularly interested in, how these things interplay. Okay? So you've got geodesics lying outside totally geodesic surfaces. How do they all interact? And so one question, and so this is just one example of the type of question you could ask about the interplay of these objects, is do short geodesics lie on geodesic surfaces? For your given manifold, does the systole lie on a surface, a totally geodesic surface? Or maybe do a bunch of short things lie on surfaces? Or maybe none of them do. Right? So the kind of question you might ask is, do short geodesics lie on surfaces, on geodesic surfaces? And I'll only refer to geodesic surfaces, so if I don't say the word geodesic, you'll know that's what I'm talking about. Lie on geodesic surfaces. Okay. So this is a potentially hard problem, and geometry is hard. And so what we want to do is leverage, when applicable, tools from other areas of mathematics, right, to bring to bear on the geometric problem. For example, for representation varieties, we can bring in some algebraic geometry to help us. And so that's what we want to do here. We want to look at arithmetic manifolds. So these are the motivating geometric questions. We need to understand arithmetic manifolds, we want to understand geodesics, we want to understand surfaces. And so that's what I'm going to talk to you about today. So in particular, the goal is to, for arithmetic manifolds, understand how to transfer concepts in the following way. So there's this web. This is how I sort of think about these things. So you've got groups, group theory. You've got geometry. You've got number theory. And often you get, in general, some things connect to other things, but for arithmetic manifolds, we sort of have connections all the way around. So we would like to understand how to take concepts in geometry and say push them over to number theory, and similarly take concepts in number theory and pull them around. So that's the goal. So this little picture here. Okay. So again, specifically the concepts of the manifolds, surfaces, and geodesics. So I'm going to just keep this board up there for the rest of the talk because it really wants to stay up there. So this will remind you our plan. Okay. All right. So let's start. Let's talk about arithmetic. So I'm going to talk in the context of three manifolds. However, most of what I'll be talking about will generalize in the appropriate way to higher dimensional things. So, hyperbolic and manifolds. Okay. So we'll let, from here on out, M is complete, finite volume, orientable, hyperbolic, three manifold. And I'm also going to say the word three-orbifold. So this is the fact then that M is going to be equal to hyperbolic 3 space modulo some gamma, where gamma is some lattice sitting inside of orientation preserving isometries. Lattice. And to make it a manifold, it needs to be torsion free. But if we don't care about getting rid of this, if we don't want to care about being torsion free, what we get is an orbifold. Okay, so the distinction is, in some ways not too significant. And right there's this Selberg lemma that says that in general, if we have if we have a lattice, we can always have a finite index subgroup, which is torsion free. So up to finite index, we can always find a manifold. Okay, so for the moment, right, we've got groups and some geometry. So the goal for the moment is to assign some number theoretical stuff. Assign number theoretical data to this picture. I should say if people have questions at any point, feel free to just shout out, interrupt. If you don't know a term or anything that I'm using, just please don't hesitate. Okay, so this is our goal. So observe. So this is the key point for this kind of geometric thing. The isometries of this guy can be identified with a matrix group. And that's really sort of what makes all this work, that you've got matrix groups. And there's appropriate generalizations if this is Hn, right? So then this is the identity component of PSO, SON1. Okay. Good. So when you're here, you can define, right? So you've got a lattice sitting inside of your matrix group, and I'm going to be a little imprecise. I'm going to sort of identify for the time being the lattice with its preimage in SL2C. So we can define just this collection where you look at Q and you adjoin the traces of elements in your lattice. Okay. So traces of gamma such that gamma is in your lattice. And for just a little bit of bookkeeping reasons, instead of just looking at all things, just look at the squares. This gets rid of some finite index stuff that you have to worry about. So this, so this thing we'll just call the invariant trace field. Of our gamma. And you can also define this following object. So, this guy sits inside of 2 by 2 matrices, so you can just add them and look at the span of this collection. Okay. So let's look here. So this same thing, you look at the K gamma span of the collection of all gamma, such that gamma is in here. And again, for bookkeeping purposes, we only look at the squares. You can look at it without the squares, and often it's actually the same. Yes?
So this gamma is in PSL2C, right?
Yes. So I'm looking at this inside of SL2. The preimage, because this preimage is just have the trace of the preimage. It's not going to change. You have a choice of two things, and so when you look at the field generated by the preimage of the two guys, it's the same. Does that make sense? And the same thing here. So you just look at the preimage. Yeah, does that? Well, you look at the trace of the preimages in SL2C and the span of the images in SL2C. Okay. Again, so this guy is called the invariant algebra. Okay. So we have some algebra sitting inside of this whole thing is going to have to sit inside of 2 by 2 matrices with complex entries. So we've got some algebra sitting inside there. This is some algebra and some field. But it turns out that these things are actually really nice. So theorem. So first of all, the trace field, it's not, it's sort of clear that field is going to be finitely generated over Q, because it's a lattice, it's a finitely presented group. So it should be finitely generated, but it's not clear that it's a number field, but in fact it is. It's a finite extension of Q, which is sort of a fantastic result. And this has to do with the fact that this group is sort of locally rigid. It actually has to do, it's sort of related to these character varieties stuff, the representation varieties. So you can, the point being is you can always conjugate your group into group matrices with entries in a number field. So this guy is a number field. This algebra is a quaternion algebra. Which I'll define in a couple minutes more carefully. But the point being is this is a very nice algebra central simple algebra, and from the setup, right, already you can see we can bring to bear number theory tools, right? There's a whole theory of stuff understanding quaternion algebras over number fields, and related to like Brauer groups and all sorts of really great things. Okay, and one other thing that I'll include in this theorem is that if gamma 1, I'm going to use this symbol to denote commensurable, so i.e. the intersection is finite index in both gamma 1, gamma 2. Okay. So if they're commensurable, then they have the same trace field, the same algebra. Okay. So the point is that this is a commensurability invariant. Now, also, I should point out, right, if two groups are conjugate, they have the same traces and the same, so these things are also the same. So, right, so we've pinpointed some number theoretical data, which is an invariant of our lattices. Okay? This is always true. And so we have from the group to the geometry, we can assign it some number theoretical data. And this is true for any lattice. Okay? Maybe I'll do a quick example. Everyone's favorite example, the figure 8 knot column. So let M8 will the figure 8 so then M8 can be identified with gamma 8, where gamma 8 is generated by the matrices sitting inside of PSL to Z, where omega is equal to -1 plus the square root of -3 over 2. And so this is third root of unity. So this group is actually very nicely behaved. We'll talk more about it shortly. But let's just observe that when you look at all possible traces of things coming from this guy, what you should get is, well, you're going to just pick out that square root of -3. That's the only thing you can really add, and you add that. So this thing is going to be q adjoin square root of -3. Furthermore, when you look at the algebra, you're just going to get all 2x2 matrices with entries in q adjoin square root of -3, so inside of 2x2 matrices. So just, even for something this simple, I scattered a few open questions for you guys to think about. So let me know if there is an answer. But as far as I know, there's no real resolution to the following thing. So open question. What fields can arise as invariant? Trace fields. For gamma of that type. So what's known is, for sure, you can get things like K with just one complex place. I'll talk to you about what this means in a moment. But specifically, as an example, imaginary quadratic extensions. Things like this. So if you have one complex place, these can arise. And we'll see how shortly. But also you can get things like Q adjoin a whole bunch of square roots. And you can get something like this from some procedure where you take things that have this kind of trace field, and then you sort of like chop them up and glue them together. So for those of you who know the kind of construction, it's sort of like a Gromov, Piatetsky, Shapiro kind of construction. For these guys, can get you a larger trace field of this type. So, but it would be interesting question to characterize what all fields can arise. Okay. Any case.
Is there a field we know cannot appear in this setting?
Wait, I'm sorry, so what? So,
is there a field?
Oh, is there any field that's known that cannot arise? Offhand, no, I'm not sure. I don't have an example of a number field that cannot arise.
Because the problem is, there's only going to be countably many, but it doesn't know which ones.
Yeah, it's a good question, yeah. I don't know offhand anything. All right. Yes?
How can you understand the K gamma and A gamma and how can you understand the functions or
so it's right. So the K gamma, the invariant trace field, right? It's just generated by these traces, but geometrically, it has to do with it's related to the gluing instructions. If you were to chop up your manifold as some ideal tetrahedra, so the sort of gluing instructions make up the traces.
is some kind of function field or conceptual?
No, it's not. It's not like it's not some function field. Yeah. No, it's just the traces of these isometries.
And also K gamma and A gamma related or
this is an algebra over this field. It's the algebra over this. Yeah. So just like for the figure 8 knot complement, right? It's the 2 by 2 matrices over Q adjoin square root of -3. Alright. So here's a theorem. The Margulis dichotomy. which says that if you look, consider this collection, the collection of all G and P, S, L to C, such that when you conjugate by gamma, you're still commensurable to gamma. Is what we call a commensurator. Either one of two things can happen. So gamma can be finite index inside the commensurator. Or two, the commensurator is dense in P, S, L to C. So there's one of two things can happen. So what you should think of is for this guy, it means that the associated manifold has lots of symmetries. So people call these the hidden symmetries. There's lots of symmetries for these manifolds, and there's not as many for these. There's some finiteness to the symmetries of these things. Okay? And so, right, this dichotomy gives you, right, these things are more symmetric, they behave a certain way. We'll call these things arithmetic. Definition. Type 2 lattices are arithmetic. So a lot of well-known examples are in fact arithmetic. So for well, maybe I'll make one remark first. So observe if gamma 1 is commensurable to gamma 2, and gamma 1 is arithmetic. Well, by this definition, this business with the commensurator, then this property holds for the commensurable thing. And you can just sort of take it, it's a little exercise. Then gamma 2 is arithmetic. So it being arithmetic is an invariant of commensurability. Finite index subgroups are commensurable, and so finite index subgroups are arithmetic. So, for example, this guy here, this is going to be arithmetic. So, for example, P, S, L to Z adjoin omega is arithmetic, since you can see the commensurator, at the very least, the commensurator of this thing this thing should at least contain PSL2 Q adjoining square root of negative 3. Right, for some basic number theory kind of considerations, it should contain this big thing. It's going to be dense. So the figure 8 knot complement, so this thing is going to be finite, it's going to have to be finite index in case these things are all finite volume, so finite volume things that's inside finite volume. So, yes?
This is definition or
You can take this to be a definition.
same definition as
The commensurator is dense.
the same as the original definition of arithmetic?
Yes, yeah, it's equivalent. Yeah, so I'm going to give another definition shortly, and it's the theorem of Margulis that these are equivalent. The consequence of this is that the figure 8 knot complement this thing is going to sit inside of here, finite index. This thing is going to be arithmetic, so this guy is arithmetic. Another couple famous examples, the Baronian link complement. Satisfy a similar kind of thing. Its fundamental group sits as a finite index subgroup of some other thing like this. And also the Weeks manifold. So this is some minimal volume kind of manifold. So all of these things are arithmetic. So here's the theorem. So in general, when you have, for any lattice, again, you get number theoretic data. But in general, maybe that data is really weak, right? It doesn't make, you can't go backwards, you don't know what you started with. But in the arithmetic case, the data over here sort of determines your data over here. So in particular, here's the theorem. So gamma 1 and gamma 2 are arithmetic. M1 is commensurable to M2. The associated manifolds, that just means they share some finite sheet of cover. This is sort of by definition the same thing as gamma 1 is commensurable to gamma 2. But the new thing is this is to be commensurable as lattices is the equivalent to the fields being the same. And maybe I'll just put here to conjugation.
Can it happen that the fields are the same as the algebras?
Yes. Oh yes, yeah. You can have the same field in lots of different algebras. So, but they can only be commensurable if they're algebra both are the same. Yeah. So the picture should say, in this context, is commensurability classes of lattices is the same thing as the commensurability classes of the manifolds. And that's the same thing as just picking a field in an algebra. And they sort of go.
You recall the definition of two manifold non-commensable?
Yeah, right. So I didn't write it down explicitly. So this is the maybe right. So if there's that two manifolds share a finite sheeted cover, and so there's like some just like fine print is that we don't up to isometry. So we can apply some isometry to this guy so that these guys share a finite sheeted cover. And that's the same thing over here. These commensurable up to conjugation, because conjugating the lattices is an isometry. So that's the fine print. But
Thing is the A gamma 1 is A gamma 2 implies the K gamma 1 is K gamma 2. Did I understand wrong?
yeah, I mean, if you were to right, I mean, the data sort of right. Yeah, you have the same field and then the same algebra over that field. Yeah. So I mean, yeah, it goes together.
Mm-hmm. Okay.
So is there any element, PSL2C element which is not in, so for the second type, the complement of the
The commensurator.
of gamma is empty or no empty?
I mean, the commensurator will always contain gamma.
Yeah, the complement of this gamma.
Oh, I see the complement. Could the commensurator be the whole space? Is what you're asking?
Not the whole space. Because so when you take the conjugation, your manifold is always isometry to each other.
Mm-hmm.
But it may, if it's not in the gamma, then the group may not be commensurable with each other. So I'm a little bit confused here.
Yeah, I guess I'm not quite sure the question. So I mean, these things are you're looking at. Yeah. So maybe. Yeah, I'm not sure I understand questions. So you're looking.
G in PSL2C which is not in gamma,
Mm-hmm.
and corrugate the gamma use this G.
Uh-huh.
And if original gamma give you a manifold M1, then this new subgroup will give you a manifold
Yes.
gamma 2,
Yes.
M2. Those are isometry to each other.
They're isometric, but the thing is that they're not. Their intersection is not finite index in necessarily finite index in both. So what that means is, right, you can look at in some sense, your manifold M, and you look at some isometry of your manifold, right? And so there's just no common finite sheeted cover of these two, right? There's once you sort of move things around. Did that answer your question?
Yeah.
Yeah? Okay. All right, good. Yeah, questions are good. All right. Very good. So let's move on. So I want to take a few minutes and talk to you a little bit more about this data, right? Because this is the new thing we introduced, number fields, quaternion algebras, and so I want you to have a sense of how to work with them or what they look like. So that you could use them potentially.
So are you going to say something about how to prove the backwards direction theorem?
No, not with this definition of arithmetic. But I'm going to give an equivalent definition of arithmetic where it's almost obvious that this is the same, and it's this deep theorem of Margulis that these two notions of arithmeticity are equivalent. So, okay. So, next part. Number fields and quaternion algebras. So, just a little bit of number theory here. So we're going to let F be a field, A and B, element of F star. So this just means F minus 0. So definition, the algebra A, which we define, we use these symbols, A, B, over F, which is equal to F adjoin two symbols I and J, where I squared is equal to A, J squared is equal to B, and IJ is equal to negative JI, so the anti-commute. So it's sort of a simple object. Pick two non-zero things, and then you just make an algebra. You adjoin two symbols, I and J, to your field such that you're basically adjoining two square roots. You're doing the square root of A, the square root of B, but you're saying that the square roots anti-commute. They don't just, so it's almost like a field a field extension, but not quite. So this thing is a quaternion algebra. So obviously you have a lot of freedom, right? There's lots of quaternion algebras for any field, right? You can adjoin all sorts of square roots, So you're probably familiar with one very famous example, what we call Hamilton's quaternions. So for example, if you adjoin negative 1 over R, you get Hamilton's quaternions, which I'll write also with bold H, not hyperbolic space. And Hamilton's quaternions. You could also say have adjoined symbols, right? The square root of 1 and 1 over R. Right? There's nothing against doing that. And, well, if you do that, you get 2 by 2 matrices. It's the same thing as 2 by 2 matrices. And as a matter of fact, these are the only two quaternion algebras over R. Okay. Sorry. All right. So, right, here's the theorem. So for any field, over any field, either A is equal to 2 by 2 matrices over R, over F, or A is a division algebra. Right, so that's the dichotomy here. But this is true in general for any field. There's one thing that's not a division algebra, that's 2 by 2 matrices, and all the rest are division.
Division is the same thing as
Well, so in this case, this is the unique division algebra over R. But say over the rational numbers, there's infinitely many different quaternion algebras, right? You can just take a whole bunch of different numbers and adjoin their square roots, right? So there's infinitely many, and they're all division algebras, as long as they're not 2 by 2 matrices.
Any field or F could be local?
F could be local, global, infinitely generated. And this is just a general fact. Yeah. Okay. And just one other thing to observe. So, observe that, well, first of all, this thing AB over F is a central, simple F algebra of dimension 4. If those words don't mean anything to you, then don't worry about it. But if it does, then that's really interesting to you. And then this algebra always embeds in a quadratic extension. At least, many quadratic extensions. So you can just you send 1 goes to the identity matrix. I goes to square root of A, negative square root of A. J goes to 0, B, 1, 0. So that's one such embedding. So if you allow yourself to join, the square root of one of those guys, it just will land it naturally lands in 2x2 matrices. And then, that's sort of what we see, like Hamilton's quaternions sit inside of 2x2 matrices with, complex entries. Okay. So this is some basic stuff about quaternion algebras. So now, we're particularly interested in quaternion algebras over number fields. So we want to give a little bit of terminology for number fields, and then we'll be ready to roll. All right, a few definitions here. So a number field is a finite extension K over Q. I'll reserve the symbol K to be number fields from here on out. So a place of K is an equivalence class of norms. And you look at, and you can put norms on a field. Okay. So we'll put the collection of all these, like a piece of K. This is the collection of all places. So every place gives an embedding of K into K sub V, its completion. good so far? Number field, you can put a bunch of norms on it. You look at the equivalence classes of these things. So when you complete a number field, you only get 3 choices. 3 things will appear. You'll either get the reals, you'll get the complex numbers, or you'll get some finite extension of the p-adic numbers. So such completions will be either C, R, or some finite extension F of QP. So norms that complete to C or R, we call them the infinite places. Norms that complete to a finite extension of the p-adics, we call a finite place. So I don't want to get into this other terminology, but I'll just say like this has to do with these norms being non-Archimedean, these being Archimedean and these being non-Archimedean norms. There's a whole theory, but not for now. Yeah. So right, these are the characteristic 0 complete fields that can arise. Okay. So let's look at an example. So first of all, Q. So Q, right, has the standard embedding into R, right, the standard completion, and it has a p-adic completion for each prime number p. Right? So that means it has 0 complex places, 1 real place, and a finite place for each prime p. Okay. So another example. So this is the field, the invariant trace field of the figure 8 knot complement. So looking at Q adjoin square root of -3. So this has one really like equivalence class of embeddings into C. You can embed this guy into C sort of 2 ways, but they're complex conjugates of each other. So we just call that one place. Right? That's one equivalence class. So there's one complex. There's no embeddings into the real. There's no such completion, so no real. And there's one. So there's a finite place for each prime p inside of the ring of integers of this guy, which is the very famous Eisenstein integers. It's the same, this is the omega from before. Okay. Good? Okay. So, right. Right, so we've got number fields, we can talk about their places. So now, let's look at quaternion algebras over our number fields. So, A over A be quaternion. So what this says is, what you can do is tensor up at every place. Okay? So this embedding here So for each place, this gives you A goes into A tensor. Okay. And this is going to be a quaternion algebra. Over the completion. So you take your quaternion algebra over your number field, you tensor it out for each finite place, or each place, you get a quaternion algebra over that completion. All right, so now, right, it turns out that quaternion algebras over these fields, in some sense, are very simple to understand. Okay. So, facts. So, over C, the only quaternion algebra that can arise, AV, is equal to 2 by 2 matrices over C. This is the only, and this is a general fact over an algebraically closed field. You can't take the square root of anything, right? So when you're joining square roots, you're just getting C back. So over C, you just have this one option. Over R, as we mentioned before, we can either have 2 by 2 matrices, or we get Hamilton's quaternions. So one division algebra. So 2 choices. And then over such a finite extension of the p-adics, you can again get the matrix group, or you can get, there is one other division algebra. It's usually not Hamilton's quaternions, it's some other kind of thing, but there's just one other unique division algebra.
So what's the division of AV? What's the division of AV definition?
It's just some other quaternion algebra, it's some division algebra.
A sub V.
A sub, oh sorry, yeah, it's the, yeah, it just meant yeah, the, yeah.
Type of PK for each B in PK.
Yes, this should be a K. Thank you. So, right, the picture again, over a number field, the division algebra is like maybe a really big mess, so you don't maybe know how to understand it. But when you look at this completion, right, for every completion, you have just a couple options, right? It's either the division algebra or the matrix algebra. And so we're going to call, if you're of this type, we say that you split over V. And in this kind, we say you ramify over this place. So that's important lingo. Splitting means you go to your matrix algebra. Ramifying says you stay division. So we're going to collect the places, the finite places where the algebra ramifies. So we're going to define ram sub f of A to equal the set of V, which we can also think of primes sitting inside of our number field. So some primes, inside of our number field such that finite places where A, V ramifies. So a couple important facts. So this collection is always finite. It can only ramify a finite number of places. And you should think of it as like an on-off switch. Like, it's just, you just flip it to one or the other. Some on-off ramifies or doesn't. So this collection is finite. It's finite. And the amazing thing, and we'll talk about this in a few minutes, is that this collection controls the geometry of the corresponding manifold, right? So right now we're spending a lot of time right here, but when we push back into geometry, the geometry is controlled by this collection. So geometry, a lot of geometry, is controlled by the finite ramification. Oh, and I should say, maybe I'll put it back over here. There's a theorem that A is totally determined by what it does here. A is determined. So if two things split and ramify at the same places, they're going to be the same algebra. So theorem, A is totally determined by this data. I mean, there's a whole theory of this stuff, and I can't go into it too deeply. But right, the point is if I say, all right, you pick the algebra that ramifies over these, 4 places, like that determines an algebra, and no other algebra has that property. So it boils down to sort of choosing, the places where you want it to ramify. Okay.
If you choose finite places, there is such algebra?
Effectively so. There's some fine print compatibility stuff. You have to have like an even number of ramifying kind of things. But yeah, I mean, it's basically, you can pick whatever you want up to some like basic conditions, compatibility conditions. All right. Very good. So this.
There is only one condition. With the number of places is even.
Yes. The number of places where it ramifies is even. Okay. Very good. All right. So one last definition. So some collection inside of our algebra is an order if it is a full rank lattice and is a ring. So, e.g., something like M2 of Z adjoin omega sitting inside of M2 Q adjoin square root. It's sort of like the thing you would think. So you've got some order in here. So it's basically like, it's sort of like, ring of integers inside of your quaternion algebra. And there's always a there's always a maximal one. And so we're going to look at that, and that's what we're going to use. Okay, so now we're ready to give an alternative definition of arithmetic. Yeah, I know, it took an hour, but we're there. All right, okay, so here's the construction. Okay, so, got to define a few things. So K is a number field with one complex place. So for example, Q adjoin I, Q adjoin square root of -3. These things, all imaginary quadratics, but also, you could imagine higher or degree extensions as well. You let A over K be a quaternion algebra that I can specify, right? It has no choice over the complex place. It's going to have to split at the complex. But I have a choice at the real places, and I want to choose the division algebra. So quaternion algebra that ramifies at all real places. Okay, so let's pick some maximal order, kind of like this guy, sitting inside of a maximal order. So, since this guy sits inside of A, it's going to sit inside of the diagonal embedding of all of the completions, right? So you look at this guy and you look at its completions, right? So the first completion is going to have to be M2C, and then all the other completions at all the other real places are a bunch of So this sort of spreads out, if you look at the diagonal embedding of this guy into here. And the point is that once you spread this thing out, that this thing is going to be discrete. Furthermore, if you look at just the guys in here that are of determinant 1, right? These are, you look at the determinant 1 things inside of this, whatever, right? There's this notion of reduced norm, but you can just think of it as these all sit inside of matrices. You just look at the determinant, all the things with determinant 1. This then gives rho sends this thing into SL2C cross SU2 cross SU2 is a lattice in that it's finite index. So finite covolumes. Okay, and so now you just project onto the first component, and you get your lattice. Okay, so we'll just project P of rho. And again, let's actually just project into the projective group. Sits inside of PSL2C. This is a lattice. So I'm going to, from here on out, something that arises like this, I'm just going to denote this with gamma subscript O, to remind us of the order, and put this 1, this one. And so we had to determine this number theoretical data. Once you get order, the order fills out, like spreads out across all the different places, and again, it becomes discrete. You know, it's not necessarily discrete. If this general procedure doesn't necessarily give you a discrete thing, you know, if you don't spread it out. I mean, here it sort of is because these things are sort of compact, but this is part of a much broader procedure for constructing arithmetic lattices. Oh, anyway. So the point is that any group gamma commensurable to this thing here is arithmetic. So there's two definitions, and really it's the theorem of Margulis that this definition is equivalent to this condition about the commensurator, this sort of geometric thing. And it's from this definition that you can see that if you have two arithmetic guys that are commensurable, right? It's sort of, you know, there's some fine tuning, but it's pretty clear that you're sort of forcing the number fields and the algebras to be the same. If you know, so commensurable groups give you, give you.
You never use the finite places through this construction.
Correct. There's no restrictions on the finite places here. The finite places come in when you look at the associated geometry of the manifold. But you don't have to use the finite places here.
So is A assumed to have at least one real place?
No, I mean so K could be right, one of these guys, and these have no real places. You don't need any real places.
So given a number field and a quaternion algebra, you may have many maximal orders, right?
Yes. Yes, you can have many. And that the fact that you can have many maximal orders is actually a key ingredient in some spectral geometry kinds of things.
Okay.
So, yes, you can have many maximal orders. But they will all be, you get commensurable kinds of things.
They will be commensurable.
Yeah.
Okay.
Just a quick example. So when K is equal to some imaginary quadratic, and A is equal to 2x2 matrices, then when you do this procedure, you maybe should pick your lattice to be the ring of integers. So what you get is, in this notation, this gamma 1 is going to precisely be PSL2 of OK, which these things are called Bianchi groups. just to say as a fact, these are not co-compact. As a matter of fact, any non-co-compact arithmetic three manifolds arises from one of these. So these sort of classify all the non-compact. So the point is that these are the collections of things where you look at the imaginary quadratics and there are no finite ramification. These are the things where, so if there's no ramification, things are not compact. They're still finite volume. But as soon as you ramify somewhere, it becomes compact. Okay. All right, so good. Are there any questions about this? Okay. Maybe just to tie this together.
One question, yeah.
Yes.
So you said if you choose a different maximal order, the lattice construct is a commensurate. That's what you
Yes.
said. So to get the different arithmetic lattice, you have to choose a different algebra then, right?
Yes. The commensurability class, I mean, this is sort of what we sort of hinted at the beginning. The commensurability class is totally determined by the number field in the algebra, not the choice of the maximal lattice. The choice of the maximal lattice may affect the isometry class, but not the commensurability class. Okay. All right, so just to tie this in, what Misha was mentioning yesterday about volumes, there's a sort of a simple, for these kinds of things, a simple volume formula. So an application of this thing. So the co-volume of one of these guys constructed in this way is equal to, this is really a fantastic result. This particular computation was worked out by Burrell in '81. So this is the discriminant of the number field, right? So something that measures the size of its ring of integers times zeta of 2, the Dedekind zeta function of the number field is 4k minus 1 times right. So this number here, right, is just composed of the discriminant, zeta function, and the degree. Right? This is entirely dependent on the field, just some number theoretic stuff about the field. And then you have the finite ramification. The more primes you ramify, the larger the volume becomes of these things. Right? You sort of multiply by more and more things. Right? So the finite ramification, the finite ramification didn't appear in the construction, but it controls the geometry in this sense.
What no P?
These are primes in the so primes associated with each finite place. Like over Q, it's sort of like finite, prime numbers in the integers.
What is no P?
Oh, the norm. The norm of the ideal, it's, just the, a number, right? Like in commutative algebra, number theory, it's the norm of that.
Is it number or?
Yes, it's a number.
Is the number quotient or?
Yeah. Right, good. And so here's construction. So we'll start with geodesics. Talk about, right. So we're starting to see how we can move around here. Right? So far we've got geometry, right? The commensurability class of our orbifold is sort of determined by this stuff, and that's coming from these groups, these lattices. So, closed geodesics and maximal subfields. And so if we have some closed geodesic sitting inside of our orbifold, that's the same thing as having some geodesic axis A sitting inside of hyperbolic 3 space, and some gamma sitting inside of big gamma such that gamma of A is equal to gamma. Right? You have some just axis upstairs, and you have some isometry in our lattice that preserves the axis. So it'll just translate it up, right? So you might move from here, you might move up to gamma of x. And so when you quotient out, you close it up, close up the loop, and you get a closed geodesic in the quotient. Okay, so this is the picture. So closed geodesics correspond to these kinds of elements inside of our geometry. Make sense?
What's the definition of axis?
Some geodesic axis.
What is the axis?
It's just a geodesic inside of hyperbolic 3 space. Yeah, just a full geodesic. You know. So.
I guess you could say it's a set of points moved to least by the isometry.
Yeah. Because at any other point the displacement is longer, so it's minimizing the displacement along this axis.
Mm-hmm.
This is the
So we call such gamma loxodromic. And are characterized by the fact that when viewed as sitting inside of PSL2C, the trace of this guy is inside of C minus this little piece of real numbers. So the trace just cannot be a real number between -2 and 2. So, fact. So, gamma inside of, I'll just say SL2C, loxodromic. Implies that this guy is diagonalizable. With distinct eigenvalues we'll say lambda it's got to be inverses because it has to have determinant 1. So the geodesic length of this quotient, when you fold up the axis, is equal to the translation length
So you also, the absolute value of the eigenvalues shouldn't be 1, yeah? To avoid rotations.
yeah, I mean the absolute value doesn't need to be 1, but I mean the product has to be 1.
No, I mean,
But
Just
just
think
think
of-
of roots of unity.
yeah, they should.
No,
they
no.
should be root. Yeah.
No.
I mean, think of the matrix.
They're not going to be roots of unity.
Yeah.
Because, I mean,
Oh, sorry. I read as a
It's only
if
one
only.
implication.
You're only doing one implication. Very good. Yeah, sorry.
okay.
I-
Okay, yeah, no problem. It's good to ask stuff. Yeah, but yeah, these things are not going to be roots of
Yeah,
unity.
no, sorry.
Yeah.
I read it as a if only. Yeah.
Okay, so the translation length, right, so how much this guy just shifts that axis up is just given by this. Okay? So the translation length, so the length of this geodesic, which we'll write like this, is equal to 2 log lambda. I mean, this is just some hyperbolic geometry stuff. You can sort of conjugate it to, like, you move, it's just some basic, it's just an exercise. Conjugate the point to like I, move it. Okay. But also, there's another exercise. This is the same thing as the real part of 2 arc cosh of trace of gamma I mean, the trace, right, I mean, you can sort of see why, I mean, the trace is the sum of these two things, right, the sum of the 2 eigenvalues, and so when you just sort of move this stuff around, this is what you would get. So the thing that you should observe is that geodesic lengths seem to be somehow deeply intertwined with the traces. Okay? And we know the traces generate like our number theory stuff, right? Our fields, our algebras. So you should see that this is starting, right? This is going to be detectable with our arithmetic data. So observe that if you look at this field, the field K adjoin lambda of gamma would join this guy. Okay? This is going to be a quadratic extension. Right? It's going to, right, because it satisfies a quadratic characteristic polynomial, right, from this condition. So but this is inherently just isomorphic. Right? This behaves like this K adjoin lambda sitting inside of our right, so it's just so right, it's I'm thinking of like R adjoin I is like the same thing as looking at sort of the thing you get when you would adjoin this thing sitting inside of like 2 by 2 matrices over R, something like that. And you see like this is like this is like, this thing is effectively I, behaves like I. And so it's like the same thing, it's just an embedding of this field inside of our matrix group. You see that? This is a quadratic extension sitting inside of our algebra. So right? We'll give this a name. So any k over k quadratic such that it sits inside of our algebra is a maximal subfield. Yeah. So I want to say just one or two things about this and then I'll wrap up. So the point is, if you choose some geodesic, some closed geodesic, what you wind up getting on the other side, okay, is a quadratic extension sitting inside of your algebra. Okay. So that's part of this picture from geometry going into number theory. And conversely, you can go the other way. Whenever you have conversely, given a maximal subfield, K, then usually, often, this the ring of integers of this K sits inside of our maximal order. Either always or like half the time. There's some fine print. But it sits inside of the order. And so this gives rise to loxodromic elements. When you do this whole big procedure in Gamma 1. So the big point, right, is that we have correspondence. Geometry gives us maximal subfields, and given a maximal subfield, we get geodesic lengths. Okay, so filling out this picture here. And so I will stop here, but next time our plan is to just mention a couple extra things about geodesic lengths, talk about surfaces, and then how to use that to solve some spectral geometry questions, right? So basically taking the spectral geometry questions and pushing them to number theory, and then using number theoretical tools to answer the geometry question. So that's it. Thank you.
Questions? Everything's clear?
This is rational order of 8. Or is
Yes, this guy is the maximal order from this construction up here. Yeah.
this 8 or 8?
Yes. Yeah, maximal order. This guy is the maximal order of one of them.
What happens when OK is not inside O?
Yeah, so it almost always is. There's this theorem of Chinberg and Friedman that give a precise description of the cases in which it might not sit inside, and it's a very restrictive. It's called a selectivity result, and in those situations, the OK sits in like half of the maximal orders, but not the other half. There's like a bunch of maximal orders.
And geometrically, is there an interpretation?
Yeah, so I mean, geometrically, what that means is you get two commensurable manifolds where one will have geodesic lengths that the other doesn't. And in fact, this is an important, has been used as a tool to construct certain manifolds that are commensurable but have sort of, and have maybe like the same volume, certain properties, but have different geodesic lengths. Great. Yeah, but this happens, it's almost always, in some sense, it sits inside there. Always, for any maximal.